So now we're going to jump into our review of what logarithms are and what their graphs look like. Before we approach logarithms, let me remind you of the symbol e. This is actually just a placeholder for a number like pi is. This is a number that came up frequently when people were working with exponential functions and they got tired of writing out the long decimal over and over and over again. And since it kept appearing, they decided to give it a name and then to also make a way to kind of abbreviate it in a sense. So just like pi goes on forever and ever, it's an irrational number. E has a value of 2.7182818, and it goes on forever and ever. I've given you the formal definition of it here, but I'm not really expecting you to need to use that in any way. So now we're going to look at what logarithms are. In summary, a logarithm is just an exponent. You use logarithms to solve for unknown exponents. So, for example, if you had something being raised to a power equals a number, and you didn't know what the exponent was, you would use logarithms to find that answer. What's very important here is being able to change back and forth between these two forms. We call the one on the right the exponential form because it's written as a base being raised to a power. And the form on the left is what we call logarithm form because it has a log in it. Easiest way to try and keep track of this is that the base of the exponent is what we call the base of a logarithm. It's like an exponent, but it's written towards the bottom of the number instead of being up high. So this is a subscript. So the base is that tiny number you'll see right after the log. If you don't see a number there, we'll talk about that in just a second as well. So the base of the logarithm is the base of the exponent. The number by itself on the other side of the equation for a logarithm, that is the power, and that's what you're usually looking for. That's why it's set up this way, because usually you're solving for the exponent, so you're plugging in these two numbers and then getting an answer for the exponent. So the number by itself is the exponent, and then the number that you're taking the log of, that's the number that's by itself for the exponential form. A couple notes for this. This does require the b value to be greater than 0. It can't equal 1 because then you're just dealing with 1 raised to a power, and 1 to any power is still just 1. And it's also assuming that our x value is positive. So b and x both positive. So now let's talk about a couple of the real quick special kinds of logs. Maybe they won't have a base written there. It'll just say log of something or ln of something. If they don't show a base, then it's a base of 10. So this is what they call a common logarithm. You would just see something like this. There is no tiny number towards the bottom after the log. So that means they're talking about something that's hinging on 10 to the third power or 10 to the fourth power, or whatever the case may be. So base 10, if you don't see a log, just like if you don't see an exponent, it's an exponent of 1. A natural log, same idea, you're going to see an ln. This stands for natural log. And no, I have no idea why it is ln instead of nl. The base for this one is e. So that's that number we just looked at on the last slide, that 2.7 value. So if you see an ln, and there will never be a base with this one, then understand that we're talking about e being raised to a power. So if you need to change it exponential form, it's going to be e to the y equals x. So now let's look at some of the properties next. You should have seen these before. These are just kind of shortcuts that are helpful to know in a few certain situations. For example, if you have a log, no matter what the base is, and then the value is of 1, then the answer has to be 0, because the only thing that gives you 1 for the answer is if you're raising something to the 0 power. Any base to the 0 power is equal to 1. Another shortcut is if you have log base b of b. Well, if those two numbers match, then the answer is going to be 1, because what they're doing is they're saying b to the first power equals b. Anything to the first power doesn't change its value. It stays as what it is. So look for the base and what you're taking the log of to match. And then here's a similar case. If you have log base b of b to a power, then the answer is just going to be the y value. It's kind of like this stuff is all canceling out. So if you have base of a logarithm and base of an exponent being the exact same number, then the answer is just going to be the exponent. And that comes from the fact that b to the y would equal b to the y. And in the last case, very similar. This one, instead of having log base b of b, this is b to the log base b. So in either case, if the base of the logarithm and the base of the exponential match, then those things just cancel out, and your answer will just be whatever the other variable is, which in this case is x. Now looking at your actual assignment, you're going to start off with just a series of very quick questions that can be answered using the shortcuts we were just looking at. For example, This one is giving us a logarithm with a base of 2, and then the exponential part is base of 2. So if you're looking at our properties, this matches the case that we have right here. We have log base 2 of 2, and here I'm telling you that as a shortcut, that answer is going to be 1, because we're basically asking you what is the exponent of the base to get that same value. So whenever the base of the logarithm matches the number that you were taking the log of, the answer is 1. Now, some of the examples in the beginning of your assignment aren't going to match any of the 4 properties you have here, and that's why I gave you this note towards the bottom of the slide. And these will apply to either common or natural logarithms. They apply to any logarithms you're dealing with. So the idea is that you want to set it up in the exponential form using the property we had in the last slide, how you convert from exponential to logarithmic, and then rewrite both sides of the equation using a common base. So see if you can write the big number like 125 as 5 to the 3rd power instead. So write them both with a common base, and then once you've done that, you can set the exponents equal to each other and solve the equation from there. So we'll look at an example of this next. So for this question, I don't see us matching any of the shortcut properties I gave you. It's not like the 2 numbers match, for example. So the idea here is we need to figure out what the exponent of 6 is. So we're saying 6 to the x power equals 1296. And that comes from how I showed you guys to convert between logarithmic form and exponential form. The base of the logarithm is 6, so the base of the exponent is 6. The value that's on the other side, and if you don't see anything on the other side of equal sign, you can just kind of draw your own in for reference. So the idea is I'm saying what is the exponent going to be? That's the power. And then what you're taking the logarithm of goes by itself when you're in exponential form. So what I need to do next is try to figure out 6 to what power equals 1296. To do this, you might need a calculator handy. Some of the numbers will be easier than others, but I can guess that I in some way need to change 1296 to a power of 6, because my goal is to get a common base for both of these. So in this case, you might just want to play around with hitting 6 times 6 times 6 and see how many 6s you have to multiply together before you hit that value of 1296. In this case, it's 6 to the 4th power. So once you get a common base on the 2 sides of the number, then you can essentially cross out the bases and set the exponents equal to each other. And there may or may not be more solving you have to do from there. In this case, we're done. My answer is just x equals 4, but sometimes you might still have to do some opposite operations to get x by itself. You will also have a few questions where you are asked to do this using a calculator, because sometimes the answer is going to be a very ugly decimal that you couldn't come up with on your own. It doesn't really matter what mode your calculator is in as far as radians or degrees or anything like that, because we're not using sine and cosine here. But do note that they will usually tell you what they want you to round your answers to. Now, the main thing I wanted to point out was this one, for example, does not have a base written on there, so you have to recognize that that means this is the assumed base 10 case. This is what we call the common log. If you want to draw your own in for reference, just to help you remember that in the beginning, that's fine. But the standard is if you don't see a base there, it is base 10. And that's what most calculators are designed to do on their own. Your calculator may vary, but if you just see a log button by itself, that's what it's designed to calculate. So you would hit log of, in this case, negative 72. And something special is happening on this particular question, because if you type it in, your calculator is going to say domain error. Now, if you get domain error, that means that there is no answer to this. It's essentially undefined. And when we look at the graphs, I'll show you why exactly this one is undefined. But if you get a decimal, just make sure you round it correctly. And that's about it for those questions. Some of them may also use natural log, and usually your calculator will have a separate button for ln. So just make sure you know how to use one function or the other in your calculator. You may also have to go into some of the menus and the mode options to find the difference between log and natural log, depending on the calculator you have. Next up, you're going to see some equations that you have to solve for whatever the variable may be. Usually it's going to be x on these. So again, you'll want to make a habit of changing these into the exponential form. So you start off by saying, what is the base of the logarithm? If you don't see a base, it's base 10. The number by itself for the logarithm, that's the power. Usually that's what you're looking for, but in this case, they're telling us the exponent is 3. And then what we're missing is what they're taking the log of, which is what goes by itself in the exponential form. Now, to solve for x, this is actually just asking us to evaluate what is 10 to the third power. So there isn't any other work we have to do on this one, but sometimes there might be more steps you have to take as far as opposite operations and isolating your answers. So basically, change your equation into exponential form and then solve the equation. The last thing we need to talk about is what the graphs of logarithms are actually based on and what do they look like. We've been talking about exponential functions, and you can see those exponential functions here. For example, y equals 10 to the x. Pretty much all of the base to the x power graphs look essentially the same. It has an asymptote at y equals 0, and it approaches that asymptote on the left-hand side, but on the right-hand side, you can see it shoots up, and it goes up forever to infinity. Now, the logarithm is actually just the inverse of this. If you remember inverses from when we covered them earlier in the year or from Algebra 2, the idea of the inverse is that it reflects the graph around the line y equals x, or it's switching the x and the y coordinates. So every time you see a coordinate on this graph, like 0, 1, the logarithm has flipped around 1, 0. So this graph is what we're focusing on in today's section. The important characteristics of it to note are that it has a vertical asymptote at x equals 0. So that means it's never going to cross into the negative values, and that's why sometimes your logarithms were undefined, because you can't take the log of a negative number. It doesn't exist on the left-hand side of the graph. And then this graph goes down forever on the left-hand side, and on the right-hand side, it increases forever. There is no horizontal asymptote on this one, because the original exponential graph just had a horizontal asymptote at y equals 0. So by flipping this, now we have a vertical asymptote at x equals 0. We're essentially just switching x and y. So everything you know about the exponential function, switch it around to be either an x, a y, or vice versa. Natural log graph and the log base 10 graph, they look almost the same. There are very minor differences in the same way that 2 to the x looks pretty much the same as 3 to the x, or 4 to the x, or 5 to the x. They're very minor differences. This one is based on the function e raised to a power. So it's not much different from doing 10 raised to a power, but it will land at slightly different coordinates. But as far as knowing the rules for it, just know that the inverse ln of x has the same idea of crossing through the point 1, 0. It has a vertical asymptote at 0. On the left-hand side, it goes to negative infinity. On the right-hand side, it goes to positive infinity. And this graph is continuous. There aren't any gaps or breaks or anything in it. So now we'll look at how to apply some of our transformation rules to these graphs. Your first few examples will just be multiple choice. I'm going to skip past those and just show you one where you actually have to graph it yourself, because I think that'll be a little bit more challenging for you. And again, the rules I'm going to utilize here will come from the transformation rules we talked about. How do you know whether a graph is being shifted up, down, left, or right? How do you know if it's being reflected, etc.? So here they've given us a function, natural log of negative x plus 4. Right off the bat, that means we need to know what the basic graph of natural log of x looks like, which I just showed you guys on the last slide. And we need to know that having a negative in front of x causes the graph to reflect around the y-axis. So it's going to flip it side to side. Then, since we have a plus 4 outside of the function, that's going to be a vertical shift, moving the graph up 4. So when we go to plot this function, you'll notice that they have a tool that matches what natural log graphs look like. They even have them labeled for you if you just hover over them. So in this case, we're interested in using the logarithm tool. So go ahead and start with your logarithm on the x-axis. It should cross at that point 1, 0 that I told you guys about. Logarithms, all of them should hit through that point unless there's some kind of a shift happening to it. Okay, next we need to look at the transformations being applied here. I told you guys that this one is being reflected across the y-axis, and that's because there's a negative sign in front of the x. If there had been a negative in front of the whole function, then it would have reflected around the x-axis. It would have been an up and down flip instead. So inside, next to the x value, that's a reflection about the y-axis. Next, they have a plus 4 value here. Since that's not being added to the x value, it's outside of the function. That's going to be a vertical shift. So I just need to take this slide bar for the vertical shift, and it went up 4 units. So you can see where my graph ends up, and now I can save my answer and check it. And that's all for the notes. I hope that will be useful on the assignment. Thank you, guys.